Hello everyone, in this video we are going to discuss the bounded buffer or producer-consumer problem in process synchronization. In this problem, we have a buffer of size n shared between the producer and the consumer process. The producer process produces an item and stores it in the buffer. The consumer process consumes an item and removes it from the buffer. The total number of items in the buffer is kept track using a variable item count. The producer process increments this item count whenever it produces an item, and the consumer process decrements this count whenever it consumes an item. So the producer and the consumer process thus share the buffer and the variable item count. So the synchronization problem here is two things. Number one, the producer process must wait if the buffer is full. Obviously, if the buffer is full, the producer process cannot produce and store an item. And the consumer process must wait if the buffer is empty. Obviously, if the buffer is empty, there are no items to consume, hence the consumer process must wait. We have to take care of this condition. And the second is, the buffer and the item count, which are shared between the producer and consumer, have to be updated synchronously. There should not be any race condition in that. The buffer must be accessed by producer process or a consumer process one at a time. And the item count updation also has to be updated by the producer or the consumer one at a time. Now let's look into the algorithm. So here we have a buffer of size n, and we have a binary semaphore mutex. The purpose of this mutex is to provide exclusive access to the buffer. So the producer process, when the producer or the consumer process access the buffer, it has to use this mutex to ensure that they do it exclusively. And then we have an integer variable, integer semaphore full. So this represents the number of full buffers, and as initially there are 0 full buffers, its value is initialized to 0. Initially there are no full buffers available, hence it's initialized to 0. The integer semaphore empty represents the number of empty buffers. So initially all the buffers are empty, right? So hence it's initialized to value n. Now let's look at the producer process structure. So here the producer process produces an item and stores it in next p. Now we know that the producer has to wait if the buffer is full, right? So here it calls wait on empty. See, in the sense, if you need to recall the wait and signal operations. So what wait does, it checks if the value of the semaphore is less than or equal to 0, it makes the process to wait in this while, right? So here, if there are 0 empty buffers, the process will wait. So if the producer process must have some empty buffers to produce and store the item, right? If it has 0 empty buffers, then it has to wait. If there are some empty buffers, that is the empty value is greater than 0, then it decrements the empty buffer count, right? So that's why the producer will call wait on empty, right? And then if there are empty buffers, it continues further. It calls wait on mutex. So this is to make sure that when it is writing to the buffer, no other producer or the consumer process will access the buffer. So the mutex will be initialized to, which is initialized to 1, will be 0. The producer process can write the item to the buffer. Once it's done, now it has to signal the mutex so that other processes can access the buffer, and then it is calling signal full. What signal does? If you see here, signal simply increments the semaphore count. Now what producer process has done is it has decremented the empty count, right? It has decremented the empty buffer count, and it has produced an item, hence incremented the full buffer count. Hence you can see the signal full will increment the full buffer count. So it has decremented the empty buffer count and incremented the full buffer count, right? So the things are opposite for the consumer, right? So the consumer has to wait if there are 0 full buffers. Hence it calls wait on full. If this full value is 0, right? If this full value is 0, it has to wait. Otherwise what it will do? It will decrement the full buffer count. It will consume an item, right? So it will consume an item and decrement one full buffer, right? So it will call wait on full. So next, it has to consume or remove the item from the buffer, right? So it has to access the buffer. Hence it calls wait mutex and locks the access to the buffer. And once it removes the item from the buffer, it will call signal mutex so that other process can access the buffer. And then now what this consumer process has done is it has incremented one empty buffer. right? It has decremented one full, it has consumed one full buffer, and it has incremented one empty buffer. So it calls signal empty, so that the empty buffer count is incremented. Exactly opposite of the producer code is the consumer code. Now let us execute the program and see. Now here we have the header files declared. We have a semaphore.h, we have a pthread.h, right? stdio and stdlib.h. We have initialized the buffer size to 10. Here we are using a pthread mutex. Okay, so it's same as your binary. It is same as your semaphores. So, but it's a binary mutex supported by pthread library, right? And then it'll by default be initialized to 1. Now we are declaring tidp for storing the thread ID of the producers, and tidc to store the thread ID of the consumer process. Here we are declaring two integer semaphores, full and empty. Full represents the number of full buffers and empty represents the number of empty buffers, right? And this item count, this keeps track of number of items in the buffer. And then we are declaring a buffer of buffer size. So these are the things we have declared. Now the initialize function, what is this initialize function doing? Initialize function is initializing all the semaphores. So pthread mutex is initialized, so it will be initialized to 1 by pthread mutex is initialized by calling pthread mutex underscore init, pthread underscore mutex underscore init. It will be initialized to 1. Now sem underscore init, it's initializing the semaphore full. Initially we have 0 full buffers, isn't it? No, there are no items in the buffer. Number of full buffers will be 0. Hence you are initializing it to 0. What does the middle number represents? That this is between the threads and not the processes. If it is for processes, it has to be 1. If it is for between the threads, it should be 0, right? We are using threads for the producer and consumer process, isn't it? So we are the middle value is 0. Now in this we are initializing number of empty buffers. What should be the empty buffers initialized to? Empty semaphore should be initialized to buffer size, because all are empty. The number of empty buffers will be equal to buffer size. And there are 0 items initially, hence the item count is initialized to 0. So this we have initialized. Now this write function is being will be used by the writer process. So what is it will be used by the producer process. So what is it doing? It is taking an item as an argument, and it is storing the item in the buffer and incrementing the item count, right? The item is stored in the buffer, in that item count index, and that index is incremented. What read operation is doing? Read operation is decrementing the item count and returning the content of the buffer, right? And this is about the read and write function. Let's look at the producer code. So the producer, it's taking the producer number as an argument, right? Here we are, it has to produce an item, right? So this item is the item produced by the producer. We are calling rand function. So rand function is going to generate a random number, and we are ensuring that the random number generated is between 0 to 10 by using mod of 10. You can use anything here, okay? You can use, or you can leave it also, right? So it's generating some random number between 0 to 10. Now what it has to do? It has to call semWait empty, right? So if there are empty buffers, the process will decrement the empty count and proceed. Then it's calling mutex log, so that it logs the write operation, right? So the producer is calling write. So it is printing producer has produced item, and it is writing that item to the buffer. We have seen the write function, right? So this item will be stored in the buffer. Now once it's done producing an item, it will unlock the mutex, and it will call signal full. Post signal function is sem underscore post in semaphores, right? Consumer process, it's opposite of your producer process. It takes the consumer number as an argument. It is taking declaring an item integer, wherein we will read the item from the buffer and store in it. Then we are calling semWait full. Only if there are some full buffers it will continue, otherwise it will wait. And then we are locking the buffer access by calling some mutex, mutex lock, right? And then it's calling read. Read will return the item from the buffer, right? And then decrement the item count, right? So, and now you're printing whatever item you have read from the buffer, right? You're printing that, and then you're calling unblock mutex and sempost empty, right? Sempost empty is going to increment the empty number of empty buffers. It has consumed one full buffer and increased one empty buffer. So in the main, what are we doing? We are calling initialize function, right? And we are asking the user to enter the number of producer process, enter the number of consumer process, and using a for loop, we are creating the producer process, right? So the producer process thread IDs are stored in this, and they are going to execute the producer process, and the consumer process, it's going to store the consumer thread IDs in this, and it's going to execute the consumer code. And then we are calling join function. This for loop will wait for the producer threads, and this for loop will wait for the consumer threads to complete. So basically, join function makes this main thread to wait for the producer process and the consumer process. Let's execute this. So number of producer process, say I'm giving here 4, and number of consumer process I'm giving, say here 3. So you can see here producer produced an item number 3. Producer produced 3, 6 and 7. These are random numbers. Now 3, 6, 5, 7 and 5 the producer has produced. So the consumer, see, it is consuming 5, which was produced by the producer, and then it's consuming 7, and then it's consuming 6, 5, 7, 6. It's not so we can see here whatever producer has produced, the same thing the consumer is consuming. I'll run it again. Say 5 and 3. So you can see producer produced 3, 6. The consumer has consumed 6. The producer then produced 7. The consumer has consumed 7. So you can see the producer and the consumer process are synchronized. The consumer is consuming the item. The output, it is outputting the item correctly from the buffer. It's not printing the same number twice or something like that. So this shows that there is a synchronization between the producer and the consumer process. So this is all about the producer and consumer synchronization problem or bounded buffer problem. Thank you.